Hey guys, Mrs. Dan's here. So, sorry I can't be with you today, but we are on lesson 2, and this video will teach you exactly how I would teach you if I were there. You just have to make sure you make note of maybe any questions that you have so that you could ask me next time you see me. Anyway, if you could copy down the objective and then do lesson 2's do now. Also, you should check your homework answers to lesson 1. Your lesson 1 homework answers are posted, and your do now is about graphing, so you should be able to do it. So you can hit pause so that you can do the do now and then check your answers with me. So before we go over the do now, I actually wanted to quickly point certain things out on your homework. I know you don't really have a chance to ask me these questions, but again, you make note of something if you have a question, so next time you see me. So what we learned about solving a system of equations graphically is that you want to graph all of the equations given to you, and you want to find out what point they have in common. And that point that they have in common is called the solution to the system. And once you find a solution to the system, you can check that common point in all equations. So on number 1, you could see the solution was 1, 2, and my checks worked. Then on number 2, the lines shared all of the points, and that's why I said that there's an infinite number of solutions. When the lines do land on top of each other, we say that the lines coincide. They coincide when they have the same slope and the same y-intercept. Something like number 3, it's like people make common mistakes about graphing these. This first equation, y equals x, we actually like to call that the parent graph. That is the linear equation that we like to compare all other linear functions to. So it's that red diagonal line. And then for some reason, some people always forget how to graph their horizontal lines. If y is 3 everywhere, and that's why it is a horizontal line, because the y coordinate at every single one of these points is 3, right? We have a -8, 3, here's a -6, 3, a -2, 3, and so on. So the points that they share is 3, 3, and you can see that the check worked. And on number 4, the point that both these lines share is -2, 0, and you could see that the checks worked. And then number 5, they share a point. But on number 6, this is one where we say there's no solution because there aren't any points that are in common between both linear functions. These lines are parallel. Remember, parallel lines have the same slope but a different y-intercept. And then the same thing happened with number 7. There was no solution. So when we look at your do now, so on your do now, you didn't have to graph these yourself. The lines were already graphed for us. We can go and label it. That would be a really good thing to do. The equation y equals -x minus 1, you can see this line here has a y-intercept of -1. It does go down 1 over 1, so this is the line y equals -x minus 1, where I guess the other line is y equals 4x plus 9. You can see that the y-intercept is at 9. You can see that if you pick a point and you go up 1, 2, 3, 4 over 1, you land on the line. So sure, these are the 2 lines graphed, and right there is the solution. So the solution to this system is -2, 1. On number 2, by looking at it, I could quickly see that there is no solution. I would like to go and label these lines, which is what? They both have a slope of -3, so the main thing to focus on is the y-intercept. Here's a y-intercept of -1, therefore this is y equals -3x minus 1, while this is y equals -3x plus 7. And then number 3, we can see that there's a solution. It is right there. I can label these lines. Y equals negative 2x minus 1 is this line. You can see it's going down to over 1, and its y-intercept is at negative 1. Therefore, this one must be y equals 4x minus 9. Notice I pointed to this and called it the solution, but I didn't label the point. Up here, I was able to label it negative 2, 1. But on number 3, I'm actually unsure of what the solution is. I have a chance of even zooming in and look at it. It's in between. It's, I don't know, a little past 1. What is it, about 1.2, do you think? And then it goes to negative almost 4, so negative 3.7 maybe. This is a maybe. Maybe? You know, maybe it's at 1.2 comma negative 3.7. What kind of answer is that to give somebody? Oh, maybe this is the answer. So we can see that when we graph things, we can clearly see if there's a solution or not, but we might not always clearly see what the solution is, right? We can see there's a solution. I could see those lines intersect, but I'm not exactly sure what that solution is. So there must be another way of finding a solution since this graphic method isn't clear enough. So do all linear systems have a solution? Obviously the answer is no. If we look at question number 2, we said there was no solution. It didn't ask us to explain, but let's do it anyway. No, because if the lines are parallel, they do not share any points. Therefore, there's no solution. And is a graph always an efficient method for solving a system? Why or why not? Obviously, the answer is no, it isn't. And it's because of number 3 of the do now, where we were able to see that there is a solution, but we were unsure of what it was. So a graph is not always an efficient method. And it's because sometimes the lines don't cross at integer values. Sometimes the lines don't share a point whose coordinates are integer values. That might be a nicer way of saying it. You can say it very simply as, you know, sometimes the lines don't cross at a nice point. I'm going to put this word nice in parentheses because what's nice? You know what I mean by nice, integer values. But sometimes the lines don't intersect at a nice point. So since lines don't always intersect nicely, there is an algebraic way of solving this, and that's what we're going to learn today. So we're going to redo question number 3 from the do now, but we're going to do an algebraic method instead of a graphic method. Remember, you can hit pause anytime necessary. If you're watching this in class, tell the sub to please hit pause because you have to get something down. Also, this is going to be in your Google Classroom, so later you can watch parts of it again on your own. Anyway, we're going to solve by substitution. That word substitution is important. Think about the English word substitute. To substitute means to replace, to put in place of. Funny enough, today I'm not there. Today there is a substitute, right? There is somebody in the room with you right now taking my place. So we want to substitute something into our equations. So when we're given two equations, both of these equations actually have y by itself. I could see in the first equation y is represented by negative 2x minus 1, where in the second equation y is represented by 4x minus 9. You can kind of say like y has a substitute. In, the first equation, maybe in like your math class, maybe y, and the substitute is negative 2x minus 1. Any place you see a y, you can substitute it with negative 2x minus 1. Now, we've done substitution in mathematics before, really when we do our checks, when we're solving equations. When you solve, I'm going to write a simple equation like 2x equals 10. When I divide both sides by 2 and I get x equals 5, I can do a check. And when we do a check, don't we substitute a 5 in place of every place we see an x? When I do the check, I would write 2x equals 10. And in place of the x, I would put a 5. And then we can see that this checks out, 10 equals 10. So we've actually used the substitution method quite often for quite a few years. Now we're substituting in a mathematical expression. We're not just substituting in the number. So right here, I'm going to say that y needs to be substituted with negative 2x minus 1. So in the other equation, any place I see a y, I will substitute the y with a negative 2x minus 1. Anytime I put in a substitute, I will put it in parentheses. Sometimes the parentheses really aren't necessary, but it's a very good habit to get into. Now, in this case, the parentheses really aren't necessary. There is a 1 in front of the parenthesis if there's anything there. And if you distribute a 1, you're left with negative 2x minus 1. And we can solve this equation now for x. Let's add 2x to both sides. I'm left with negative 1 equals 6x minus 9. Let's add 9 to both sides. And I have 8 equals 6x. Let's divide both sides by 6. And I'm going to leave my answer as a fraction. 8 over 6 is an improper fraction. That's not simplified. I don't mind that it's improper, but I do want to simplify it to 4/3. I could, of course, write it as 1 1/3. Yes, 1 1/3 is the same thing as 1.1 repeating. Repeating decimals don't work out so well a lot of times, though. So I just want to leave it as a fraction, and I actually prefer the improper fraction over the mixed number. Once you do this, you're not done. So we need to remember that we're trying to solve a system of linear equations. And we need to remember what we learned in lesson 1, what we actually just did in our do now, that the solution to a system of equations is the point that they have in common. So my goal is to find a point. Points have x, y coordinates. Right now, I found that x is 4/3. I found part of my coordinate. Again, you could write it as 1 1/3 also if you wanted to. But I only found the y coordinate. I didn't find the x coordinate. So now I have to do another substitution. So this algebraic method, I'll agree, is lengthy, right? So I took one equation and I substituted a negative 2x minus 1 in place of y in the other equation. I solved for x and I got a value for x. But I'm not done because I need a value for y. I take this x value and substitute it back into one of the original equations. It actually doesn't matter which equation you substitute it into. Either one of them will get you the y value, because remember, we're trying to find a point that's in common. So if it's in common, it's actually on both lines. I usually always substitute it back into where I put my box. So now I'm going to write down my top equation, because that's the one I feel like substituting into. And in place of x, I'll put the 4/3. Again, get used to substituting in parentheses. And you would be allowed to use a calculator if you need to. I don't need to. I know -8/3 is the same thing as -2 2/3. And when I take away 1, I get -3 2/3. I found my other coordinate, -3 2/3. So the solution is 1 1/3, comma, -3 2/3. Okay, wait a second. What did we guess on our do now? -1.2. I said that 1.2 is pretty close to 1 1/3. Remember I said that 1 1/3 is actually 1.3 repeating? So close, not perfect. -3 2/3, it's pretty close to -3.7. -3 2/3 as a decimal, it's -3.6 repeating. Again, not crazy about the repeating decimals because you can't plug them in. You can only plug in fractions when you're substituting. After I solve, I would have to do a check. So the steps for what we just did are all written down here. You can refer back to this page, page 8, to remind yourselves of what you do. So the first step is to solve one equation for one of the variables if necessary. In this case, it wasn't necessary. We will do a question where it is necessary. And then you rewrite it with your substitution. And then we solve. That's when we got that x is 4/3. And then you substitute that value back in, and that's when we got our y is -3 2/3. And you write it as an ordered pair, and then you do a check. So let's do, I'm going to skip to number 2 down here, because I need to show you how to do an equation where maybe it's not set up perfect for substitution. Maybe I'll do number 1 before I do number 2, actually. I guess I will go in order. I want to show you that example number 1, I can quickly substitute. I can see that the second equation is set up to have a substitute. It's telling me that y is 3x minus 1. So in place of y, I substitute that 3x minus 1. So I'm going to rewrite the first equation with the substitute in it. I'm going to come all the way over here because I know there's not a whole lot of room on this page. And if I'm going to do all 3 of these questions, I need some more room. I might not do all 3. We'll see how much time allows. So 4 times the substitute equals 12x plus 4. Sometimes people ask me, how do you know where to substitute, Mrs. Dans? Well, since it says y equals, I have to put it in place of y. And then we distribute. Ooh, this is one of those interesting questions. I noticed right away this has no solution. If you don't notice it yet, you might want to subtract 12x from both sides. But I'm left with -4 equals +4. You say, what the heck is that? This has no solution. So I really didn't need a whole lot of room for this problem. If a system of equations has no solution, it means when graphed, these lines would be parallel, right? Parallel lines is what this picture would look like, because a no solution means it doesn't share any points. How do you draw lines that don't share points? Oh yeah, they'd be parallel lines. So just by knowing that there's no solution, without even graphing this, I know that the lines are parallel. And you find out quickly doing an algebraic method whether there's no solution or not. I actually think I'm going to skip number 2 for now. You know how I said I wanted to do number 2, and I do, but I want to skip it for now, and I want to go to number 3. On number 3, the second equation is set up for substitution. In this case, though, x is going to be the substitute, not the y. It's all right that something gets substituted for x. It's kind of like your social studies teacher is out now, right? There's all different things that can have a substitute. Since x has a substitute, we're going to substitute this in place of x. So I rewrite the first equation with the substitute in. And then I distribute. And I'm already noticing this is going to be interesting also. So if I combine these like terms that are on the same side of the equation, negative 2y plus 2y, isn't that 0y? What the heck is 0y? It means 0 times y. It just means 0, right? So I don't have to write it. I have 0 plus 10 equals 10. I have 10 equals 10. Oh yeah, that's true. But what the heck is x? Remember, when your variables seem to go away and you're left with a true statement, this means that there's an infinite number of solutions. Remember what a graph of an infinite number of solutions looks like. It means that I'll have one line that lands right on top of another line. These lines coincide. Remember that fancy word I talked about when we were going over the homework? To coincide means to land on top of each other. They share every single point. Kind of glad I saved number 2 for last. Number 2 is going to have some more work necessary, so I could use the rest of this page to do number 2 if I need it. First of all, first problem is that I don't see a substitute. Neither one of these equations has x by itself or y by itself. In example 1 over here, y was all by itself, so I knew to substitute in a 3x minus 1 for y. In example 3, x was all by itself, so I knew to substitute negative y plus 5 in for x. I do not see x or y by itself. So I need to fix one of the equations. I need to make a substitute. I need to decide what variable is going to have a substitute. It could be either x or y in either equation, but there is a good way of doing this. It's best to find the variable that has a coefficient of positive 1. So right here, this y is what I want to have the substitute. I want to solve the second equation for y because it's the easiest thing to do. All I have to do is subtract 4x from both sides, and I get y equals negative 4x plus 24, and I can say, done, I found my substitute. My substitute is negative 4x plus 24. And that substitute will go in place of y in the other equation. Now, some people say, but Ms. Stans, why did you solve for that y? Why did you get y by itself? It was the easiest thing to do. You want to do things that are easy. Do you really want to torture yourself? If I tried to solve for this x, I would have to subtract y from both sides, then I'd have to divide by 4, and oh my gosh, dividing by 4, I'd probably have a fraction someplace. So you don't want to solve for something difficult. Who wants to make things difficult? So you find the variable whose coefficient is 1. That's what makes things easy. So keep it easy. Let's rewrite the top equation with the substitute in there. And now let's solve this equation. common mistake is right here. That's a -3. Remember, -3 is getting distributed. -3 times -4x is a positive 12x. -3 times positive 24 is negative 72. Remember, you are allowed to use a calculator if you need to. On the left side, I want to combine like terms. I get 14x minus 72 equals -2. I know for a fact this has a solution. I'm not going to have anything weird happen like on example 1 or example 3. Let's add 72 to both sides. 14x equals 70. Let's divide both sides by 14 so that we get x equals 5. All right, remember we're trying to solve a system. The solution to a system is a point. I have an x value. I don't have a y value yet. You want to substitute again. So the substitution method, remember, means that you substitute twice. I take this now and substitute it back into one of the equations. I prefer to substitute it into the box. You are allowed to substitute it into any of the other equations up above. So I get y equals -4 times 5 plus 24. So y equals -20 plus 24, which means that y equals 4. My solution, if I did things correctly, is 5, 4. The only way I could tell if I did it correctly is by doing a check. I can hope I did it right, but I really want to check it. When you check, you must check in both original equations. You must check in both original equations. Right up here, the original equation has to be checked in the original, not like where I put my box in this case, because I altered that equation. I like to write check number 1 and check number 2 so that I don't forget to do a check, and I rewrite each original equation. So I do one check at a time. In place of x, I put the 5, and in place of y, I put the 4. My first equation checked, and again, in place of x, I put the 5, and in place of y, I put the 4. And it checked. So, solving a system of equations by substitution, if it has one solution, can be lengthy, right? Look at all the work that we did. If there's no solution, you find out rather quickly. If there's an infinite number of solutions, you find out rather quickly. And just by knowing what kind of solution, you actually kind of already have a picture in your head as to what the graph would look like if they asked us to graph it. No solution looks like parallel lines. Infinite number of solutions looks like one line on top of the other. When there's one solution, like in example 2, you know that these two lines are going to cross and meet at the point 5, 4. And that's it. I would like you to practice some on your own, and that would be your classwork here. And I'm actually going to provide you with the answers to the classwork. Not all of my work, just a list of answers, and you can check to see how well you did. Your homework really is from the textbook. I want you to write this down, please. If there is one solution, you must do checks. Remember, there's two checks because there's two equations. If there's no solution, there's no check to do. If there's an infinite number of solutions, you don't have to do the check because a whole lot of things would work. All right, so your homework really is from the textbook. You are going to try a few of these, and I'm going to put up the answers. When you hand your work in to me on Google Classroom, I need to see the notes that we just took, and I need to see your homework completed. The classwork problems are not mandatory for you to submit. You can if you want to, and I'm going to make it actually bonus points. So this assignment is going to be worth 2 points. If you do all the classwork, I can give you an extra 2 points. So it kind of makes up for if you missed an assignment. So that's it. I'll talk to you soon. Bye.